Assalamu alaikum students. Hope you are all fine by the grace of Almighty Allah. This is our fourth lecture. I welcome you all to the fourth lecture of Thermodynamics 2. Lecture 4. The contents of lecture 4 are properties of pure substance, phase change process of pure substance, property diagrams for phase change process, property tables for phase change process, conceptual questions and answers. Pure substance. What is a pure substance? A substance that has a homogeneous and invariable chemical composition throughout. It may exist in more than one phase, but the chemical composition is the same in all phases. Example: water, nitrogen, helium, and carbon dioxide. A mixture of various chemical elements or compounds also qualifies as pure substance as long as the mixture is homogeneous. As air is a mixture of several gases, but it is considered to be a pure substance. So, as you know that air Air contains nitrogen, oxygen, noble gases, carbon dioxide. So it's a mixture of several gases, but it is considered to be a pure substance. A mixture of oil and water is not a pure substance. Since oil is not soluble in water, it will collect on top of the water, forming two chemically dissimilar regions. So this is a non-homogeneous. Non-homogeneous. So as discussed previously, it is requirement to be homogeneous to be a pure substance. Air is a mixture of several gases, but it is considered to be pure substance. As discussed earlier, nitrogen, which is also the part of air, is individually considered as pure substance as well. Air in the gaseous form is also considered as pure substance. Now, these are two very important examples. In example 1, a water in two different phases is shown in liquid phase and in vapor phase. So a mixture of liquid and gaseous water is a pure substance. So water can exist in both liquid and gaseous phase and it is considered to be a pure substance. Whereas in example B, air is shown in two phases. This is liquefied air and on the top of that this is gaseous air. So it is written a mixture of liquid and gaseous air is not a pure substance. Why? Water in two different phases is considered to be a pure substance, whereas air in two different phases is not considered to be a pure substance. The answer is that the composition in example 1 H2O. So liquid and vapor, the composition remains same because on a whole this is only one component or a compound, whereas in the case of air, air is a mixture of different gases like nitrogen, oxygen, carbon dioxide and some other noble gases as well. So the composition of air in gaseous phase, example nitrogen is 78%, oxygen is 21%, carbon dioxide is 0.04%. But liquid air, the concentration of these gases changed. Therefore, air, a mixture of two phases, liquid air and gaseous air, is not considered to be a pure substance. So it is mentioned here, the composition of liquid and vapor phase in air is not the same. That is why air, when it is considered to be a two phase, it is not a pure substance. Saturation temperature and saturation pressure. So first we will discuss about the definition, what is saturation temperature and what is saturation pressure. Saturation temperature, it is represented by TSAT, sat, T for temperature, SAT for saturation. Temperature at which a pure substance changes phase at a given pressure. And saturation pressure, it is represented by P-sat, P for pressure and SAT for saturation. Pressure at which a pure substance changes phase at a given temperature. Now we will read this statement. Temperature at which water starts boiling depends on the pressure. If the pressure is fixed, so the boiling temperature is also fixed. And the example is water boils at 100 degrees centigrade. So as you know that the freezing point of water is 0 degrees centigrade and boiling point is 100 degree centigrade. At 0 degrees centigrade, water from solid to liquid, solid is ice and its liquid phase water, and at 100 degrees centigrade it changes from liquid to vapors. So from the definition of saturation temperature, phase change. So at 0 degrees centigrade and 100 degrees centigrade, both these temperatures are phase change temperatures for water. But you have to remember that, let me write T-sat and T-sat, that T-sat saturation temperature depend on the pressure. If we raise the pressure, the T saturation temperature will also increase. So the value of 0 degree centigrade and 100 degree centigrade is at the rate of 1 atmospheric pressure of 1 atmospheric pressure. So the phase change of water at 0 degree centigrade will occur at when the pressure is 1 atmospheric pressure. If we increase that pressure, external pressure, so the water, the ice might not melt, so it will require a higher temperature. Similarly, for boiling or vaporization, 100 degree centigrade will also increase if we increase the external pressure. So you have to remember the basic difference. So it takes a large amount of energy to melt a solid or vaporize a liquid. So what type of energy is required? It's a latent heat for phase change process. For solid, enthalpy of fusion, and for liquid to vaporize, it required enthalpy of vaporization, which we have already discussed in the previous slides as well. This is a line graph as shown that 1 atmospheric pressure is equal to 101 kilopascal, 1 atm equal to 101 kPa, or normally we can also take it as 100. So let me make a line. This is approximately, yeah. So you know that at 100 kilopascal pressure, this is a point, so the P saturation temperature is 100 degrees centigrade. So if let's suppose that is a line, so if the pressure is 400 kilopascal, we have increased the external pressure to 400 kilopascal. So now we see that the boiling will start at approximately 150 degrees centigrade. So the saturation temperature depends on the saturation pressure. So on the right hand side, this is a table 3.1 of your book. On the left hand side, temperature are written, and on the right hand side, saturation pressure in kilopascal are written. So for 100 degree centigrade saturation temperature, 101 kilopascal external pressure or saturation pressure is required. Now, for example, if you want to boil the water at 30 degree centigrade, so 4.25 kilopascal pressure is required as saturation pressure or external pressure. You have to reduce the external pressure to 4.25 kilopascal, so then the boiling will start or vaporization will start at 30 degrees centigrade. So now consider this is a straight line. Here water is in the form of ice, minus 15 degrees centigrade, 0, 0, 100, 100 and 250 degrees centigrade. All these temperatures are in degree centigrade. So at minus 15 degrees centigrade, the water is in the form of ice, that is solid. And if we increase the temperature and provide thermal energy to the system, the temperature of the system will rise and it will reach to 0 degree centigrade, but will remain in the solid phase as well. Now that 0 degree centigrade is saturation temperature for water. So here the temperature will, this process is isothermal, temperature will be constant and all the solid or ice will turn into liquid water. Then again we will keep on giving energy, and at 100 degrees centigrade the water is in liquid form. This again is saturation temperature T set. So this process again, this again, both are isothermal process or phase change process. So the temperature will remain constant and liquid water will turn into vapors. And when we keep on giving energy, this is a superheated region. So in all this area, this is solid region, whereas in this area this is solid plus liquid. In this area this is liquid region, this liquid plus vapors, and this is vapor region. Now you have to remember this example, so we will use this information in the upcoming slide. So for example, I will make a temperature graph. From minus 15 degrees centigrade temperature will rise. At 0 temperature will become constant, it's a straight line. Then it will rise up to 100 degrees centigrade. At 100 degrees centigrade it will become constant again, this phase change process, and then this is a line for temperature. You should know how PV or TV diagram was made, and that's the 0 degree centigrade, 100 P or T. TV diagram and PV sign, 100 degree centigrade and 0 degree centigrade. Both PV diagram and TV diagram has same trend, because we know that in previous slide we said that as the pressure rise, temperature also rise. T saturation temperature depend on saturation pressure. Therefore the trend for PV diagram and TV diagram is also same. So now these are some definitions: compressed liquid and saturated liquid. What is compressed liquid? Compressed liquid is also known as subcooled liquid, a substance that is not about to vaporize. Now remember the line that we have plotted in previous slide: minus 15, 0, 0, 100, 100, and let 250 degrees centigrade. So that region, here water is in liquid form and not about to vaporize. So this region from here to here, sorry I am drawing all this with the help of mouse, so it's a little difficult to draw. So that region is the subcooled region. So subcooled or compressed liquid. So in this region there is no vaporization will occur. So subcooled liquid temperature is lower than saturation temperature, as saturation temperature is 100 degrees centigrade. And that is the saturation temperature. So temperature is in the subcooled region, temperature is less than T set. So that is important point, might be asked in the MCQs. What is the range of temperature in the subcooled region or compressed region? Pressure is greater than the saturation pressure for given temperature. So that is state 1, P atm, 1 atm, pressure is 1 atmospheric and temperature is 20 degrees centigrade. You know that water, the saturation temperature at 1 atmospheric pressure for water is 100 degrees centigrade, so it is well below, very less than 100 degrees centigrade. So it lies in compressed liquid region. Saturated liquid. So at 100 degrees centigrade, saturated liquid, a liquid that is about to vaporize. So (100 degrees centigrade). At 1 atm pressure and 100 degrees centigrade, water exists as liquid that is ready to vaporize. You know that here we kept on raising the temperature, and at 100 degrees centigrade, water is in liquid and about to vaporize. That liquid is known as saturated liquid. Now, saturated vapor and superheated vapor. So you must remember that line. Minus 15, 0, 0, 100, 100, 250. So now that point is saturated liquid, and this point is known as saturated vapor. That vapor that has recently from liquid to conversion into vapor, or consequently, or in the reverse form, you can say that a vapor that is about to condense. So when we see from this side, this is a liquid that is about to vaporize, and when you see from this side, this is a vapor that is about to condense, vapor that is about to turn into liquid. So that is known as saturated vapor. So as already discussed, that this portion, I will change the color. So this portion contains liquid plus vapors. So this is region of saturated liquid vapor mixture, the state at which the liquid and vapor phases coexist in equilibrium. So the portion that is mentioned here in green color is the region of saturated liquid vapor mixture. Now what is superheated vapor? So when we keep on raising the temperature above the saturation temperature, like here 250 degrees centigrade, that is known as superheated vapor. So that is not about to condense, because that is a very huge temperature difference. So therefore that is known as superheated vapor. It is similar, as you can understand, that in subcooled liquid or compressed liquid that is not about to vaporize. Similarly, in superheated region, that is subcooled, and that is superheated. Subcooled not about to vaporize, and superheated not about to condense. superheated. So you have to remember all the uh, how we denote and what are the properties and concept should be clear. The TV diagram, temperature volume diagram. So I have discussed this diagram in the previous slide as well. So you have kept on increasing the temperature this at this stage. Phase change process start and the temperature become constant. So you should know what this gap means. This is the energy required to change the phase from liquid to vapor, that we have studied at LV, latent heat of vaporization. So this is a TV diagram of water. So that is a critical point and the pressure is 22.06. Okay, we will discuss it later. So this is also a TV diagram. A dome portion is shown. This dome contains saturated liquid vapor region. So we will only discuss the main point, that is the region where only liquid. This left hand line, saturated liquid line, that is a critical point. On the right hand side, saturated vapor line. So what is this? That is the energy required to change the phase of substance from liquid to vapor. This is latent heat. You will provide this latent heat to change the phase of substance from liquid to vapor region. Now as you go up, temperature becomes higher, this latent heat is reduced. Value of LV is kept on reducing, and the significance of critical point is that this is liquid portion, that is vapor portion. So as the temperature is increased above the critical point, the value at the critical point, the value of latent heat of vaporization becomes 0. So no heat is required to convert latent heat, no latent heat is required to convert to vapor, that is directly converted into vapor. So this might be asked in the MCQs, what is the value of latent heat of vaporization at critical point? And latent heat kept on decreasing as we increase the temperature. So that you should know, that is superheated region. Now for water, some values are mentioned. P critical, that is the critical pressure, critical temperature, critical volume. So this is a diagram for water, H2O. So what we see that if we keep on increasing the temperature, this is a critical point as shown here. At critical point, the value of a temperature is 373.95. As the temperature is increased beyond this temperature, as the temperature is increased beyond the critical temperature, the liquid phase of water will directly convert it into vapor phase. So these values are very important. So the pressure for water, critical pressure for water is 22.06 megapascal. Temperature is 373.95 and volume is 0.003106 meter cube per kg. The PV diagram, pressure volume diagram. So as I have discussed in the previous slide as well, The trend of temperature volume diagram and pressure volume diagram is approximately same, because the saturation temperature depend on the saturation pressure. So the important point you have to remember is that is the critical point, as we have discussed. Left hand side is compressed liquid region, the line up to the critical point is saturated liquid line, and on the right hand side that is saturated vapor line. On kept on the right there is superheated region. Here the trend of temperature and pressure line, you have to remember that. What are the trend of, that is constant temperature line. Temperature became constant because that is a phase in process. So the temperature here and here is constant, whereas kept on changing. Okay, the trend of TV and PT. In TV diagram you see that the pressure was like this, and in PV diagram the temperature trend is like this, downward trend and upward trend. In TV diagram that is a trend of pressure, and in PV diagram that is a trend of temperature. So you have to remember what are the trends of different properties. And now the second thing you have to remember, the type of PV diagram. There are two types of substances. So as you know that water, you have studied the anomalous behavior of water. This topic is included in the FSC, so you must have studied this topic. What this topic suggests that when the water has the maximum density at 4 degrees centigrade. This is a density diagram of water. I will make it a little better. So this is the density diagram of water, and this is the value at 4 degrees centigrade. So this is the value at 0. So normally when we supply heat to a substance, the volume increases and density decreases. Volume is equal to inversely proportional to density, specific volume. So but in case of water there is an anomaly. Water expand up to 4 degrees centigrade, the density water increase up to 4 degrees centigrade. That is the increase in the density. That is a density graph, and that is x-axis, that is the temperature. So the volume will reduce first and then increase, or density will increase and then decrease. So at 4 degrees centigrade the density is maximum and volume is minimum. So that's why it is written a PV diagram of substance that expands on freezing. So when you are decreasing the temperature from 4 degrees centigrade to 0, the density is decreasing whereas volume is increasing. That way it is written expand on freezing, such as water. So there is a little difference between PV diagram of normal substance, normal pure substance, and water. And the second thing you have to remember, you must see the slope of this line. The slope of liquid vapor line or saturated liquid line is negative. Okay, as you can see that are straight lines and that is not, it's an at angle. We will discuss this property in the PT diagram as well. You will understand that more easily. At triple point pressure and temperature, a substance exists in three phases in equilibrium. So what is a triple point? A triple point is a temperature where solid, liquid and gas vapor phase coexist in equilibrium. So these are the temperature and pressure triple point. 0.01 degree centigrade, or you might say 273.16 Kelvin, and pressure is 0.661 kilopascal. So you will understand it more easily when we are discussing the PT diagram. The PT diagram, pressure temperature diagram, often called the phase diagram since all three phases are separated from each other by three lines. Okay, as mentioned here, solid on the left hand side, this is a solid, this is a liquid portion, and that is a vapor state. Okay, this point, the point where all three phases coexist and meet, is known as triple point that we were just studying in the previous slide. So the pressure mentioned in the previous slide is 0.6117 and pressure is in kilopascal, let's suppose. Then 0.661 kilopascal is the pressure for water, that is for water H2O, and the temperature is 273.16 Kelvin. You must remember this might be asked in the MCQs as well. What is the triple point pressure and what is the triple point temperature for water? Now you are seeing this one is dotted and one is green joint line, and one is dotted line. So that substance that expand on freezing, example water, and contract on freezing other substance like nitrogen or other substances, nitrogen, helium, etc. So as you increase the pressure and temperature, you reach the triple point, and that is a trend of water and that is a trend of other substance. So when you draw a slope in mathematics, you have read about the slope. So the slope of water is like this. Negative slope, that is a negative slope, whereas for other substance the slope of fusion curve is, this is also known as fusion curve. Fusion curve. So the slope of fusion curve for other substance is positive. So that is the same critical point we have discussed about it. So if the temperature or pressure is above the critical point, the liquid will directly convert to vapor phase. So that is a solid phase, and now that is a triple point. One more important thing you have to understand, that below, because the liquid phase ends here, so if the temperature is below critical point or pressure is below critical point, like if the temperature is 250 Kelvin, that is less than the critical, that is a triple point temperature, and the pressure is below triple point 0.600 Kelvin, kilopascal, so the ice will directly convert into vapor. Solid phase will directly convert into gaseous phase. That is the example of dry ice. So the things you have to remember in this diagram, I will repeat. The curve of water is fusion curve. The slope of fusion curve is negative, whereas the slope of fusion curve of other substance is positive. What is critical point? If the pressure is above and temperature is above the critical point, the substance will directly convert into vapors, and if the pressure or temperature is below the triple point, then the solid will directly convert it into vapor. So, sublimation line separate the solid and vapor region. That is a sublimation line. That is sublimation line. That is a solid region, and that is a vapor region. Vaporization line. This is the vaporization line, and that is a sublimation line, and that is a vaporization line. And melting or fusion line, that is the fusion line for other substance, that is the fusion line of water. Separate, that is a solid portion, and on the right hand side of fusion line, that is a liquid portion. So that is mentioned here, that sublimation line, vaporization line, and fusion line separates the different regions of substance, different phases of substance. Substance at high pressure can exist in liquid phase at temperature below the triple point temperature. So that is also, if the temperature is higher, so temperature below the triple point temperature can exist here, right hand side. So if we are in gaseous form and gaseous phase, if we increase the pressure, so at temperature below the triple point, so the substance can exist in liquid phase as well. Water can exist as liquid at minus 20 degrees centigrade at 200 megapascal pressure. If we kept on increasing the pressure, the water can exist, because that is a negative slope line. So water can, you can see that is a triple point, but the slope is negative. That why if we kept on increasing the pressure, that is the liquid phase. So water can exist at minus 20 degree centigrade at 200 megapascal. If we increase the pressure, the saturation temperature we can decrease it. Property table. For most substances, the relationship among the thermodynamic properties are too complex to be expressed by simple equations. Therefore, properties are frequently presented in the form of tables. Some thermodynamic properties can be measured easily, but others cannot and are calculated by using the relation between them and measurable properties. Result of these measurements and calculations are presented in tables in convenient format. So we are talking about like steam tables. That tables are present usually at the end of books, and you can for certain saturation temperature you can find different properties like internal energy, enthalpy, specific volume, pressure, etc. For each substance, thermodynamic properties are listed in more than one table. A separate table is prepared for each region of interest such as superheated vapor, compressed liquid and saturated mixture region. So before you consult any table, there is a heading for which region that table is meant for. So you must read that either that is meant for superheated vapor region, compressed liquid region or mixture vapor liquid vapor mixture region. So that is an example. At the right hand side you can see this is a table. Temperature, different temperature and saturation pressure against the temperatures of saturated liquid. V is specific volume. What is Vf and Vg? So you must remember that is a critical point. Saturation liquid line, left hand side, and right hand side saturation vapor line. The values on this line, saturation liquid line, are represented by subscript Vf. That is specific volume at saturated liquid line, and these properties are represented with subscript F, and on the right hand side subscript G. So if you are given Ug, internal specific internal energy for saturated vapor line, and Uf specific internal energy for saturated liquid, and Vfg is the difference between them. So the difference between these is represented by Fg. Subscript F is used to denote properties of saturated liquid, whereas subscript G to denote the properties of saturated vapor. Enthalpy of vaporization, latent heat of vaporization, amount of energy needed to vaporize a unit mass of saturated liquid at the given temperature and pressure. We have discussed about this in the previous lecture. It decreases as the temperature and pressure increase and becomes zero at critical. That is a very important statement. Saturated liquid vapor mixture. During a vaporization process, a substance exists as part liquid and part vapor. That is, it's a mixture of saturated liquid and vapor. That's it. Inside the dome region consists of vapor and liquid mixture. Quality X, the ratio of the mass of vapor to the total mass of the mixture. Quality is between 0 and 1. So what is quality, or it is also you can might say see dryness fraction. It's the indicate the mass fraction of vapor in liquid and vapor in mixture. So X is the mass of vapor divided by total mass. Formula is written here. A two-phase system can be treated as homogeneous mixture of convenience. So saturated vapor Vg, specific volume of saturated vapor, and saturated liquid, specific volume. So the properties and dryness fraction you can calculate by this formula. So now conceptual question and answer. The question is, if the pressure is smaller than saturation pressure at a given T, what is the phase? The answer is, for a lower P, we are below the vaporization curve and it is superheated vapor region, that is gas phase. So that is the triple point of water that contains a P saturation, and that is a superheated region. If the temperature is below that, if the pressure is below that, then we are in superheated vapor region. The next question is, an external water tap has the valve activated by a long spindle. So the closing mechanism is located well inside the wall. Why is that? So there is a tap and its activative mechanism is, that is a wall and inside. So by having a spindle inside the wall, the coldest location with the water when the valve is closed is kept at a temperature above the freezing point. So inside the wall the temperature is greater than 0 degree centigrade. If the valve spindle was outside, there would be some amount of water that could freeze while it is trapped inside the pipe section, potentially rupturing the pipe. So as we have discussed, the density or volume, that is the density graph, and the other is volume density. Density increase up to 4 degrees centigrade, whereas volume 4 degrees centigrade. So that is a volume that is increased at 0 degree centigrade. So if there is water in the pipe, so the volume will increase and there is the chance of rupture of pipe. What is the lowest temperature approximately at which water can be liquid? So at the border between, here you can see that this PT diagram from the book, there are different solid regions are shown: ice 1, ice 2, ice 3, ice 5, 6, different trends. So here I have make this line, and you go up through this line, you find this point. So the temperature is approximately 250 Kelvin or minus 23 degrees centigrade. So that is a normal case atmospheric triple point of water, and there are multiple triple point of water. So I will also show a paragraph from your textbook as well. You can see that. Finally, it should be pointed out that a pure substance can exist in a number of different solid phases. A transition from one solid phase to another is called allotropic transformation. This figure is figure 3.7. So A pure substance like water can have a number of triple points. You should remember that. But only one triple point has the solid, liquid and vapor equilibrium. Other triple point for pure substance can have two solid phases and a liquid phase, two solid phase and vapor phase, and three solid phase. So point to remember is that there can be a multiple triple points. This is a figure from book. It was not much clearer, so that is figure from Google. So as you can see, that is also a triple point. That is another triple point of H2O. So the temperature is approximately 250 or 255 Kelvin. So water can exist in liquid form up to minus 23 degrees centigrade. Okay. Another conceptual question. Some tools should be cleaned in water at least 150 degrees centigrade. How high pressure should be? So you know that if you want to clean tools from water which is at temperature greater than 100 degrees centigrade, which is the boiling point of water, so you should have a temperature that is different. So what is the answer? If we need liquid water at 150 degrees centigrade, because you have to clean the tools, so you need a water that is in liquid form. We must have a pressure that is at least saturation pressure for this temperature. From steam table, this for the temperature of 150 degrees centigrade, the pressure is 475 kilopascal. So usually the 400 degrees centigrade P sat is 1 atm or 101 kilopascal. So if we want to clean our tools, so pressure must be above this saturation pressure, so the water can exist in the form of liquid. Lecture 4 home assignment. All students are advised to go through example problems from each topic discussed during the lecture. All students must submit handwritten lecture summary report minimum of 3 pages before the commencement of next lecture. Student can take picture and scan report and send it to my email address, that is arslan@ciitwa.edu.pk. All students are advised to keep hard copies of every assignment and report, as they have to submit them later when they will come to university for examination. All students are advised to prepare previous lecture thoroughly before the online video session, as there will be a viva and oral question answer session for every student. Okay, thanks a lot and keep safe. Keep yourself safe and keep others safe as well. Thank you very much.